Let's say we have a relation teach with the attributes model ID, teacher ID, and fname. So we would say that model ID functionally determines teacher ID, and the teacher ID functionally determines the teacher's first name with the attribute fname. So we have two function dependencies in this example here. Typically what happens, we put curly braces around them and call them a set of function dependencies f. Now, to make it possible for me to explain it, I will get a little abstract here and replace the names with letters. As you can see, instead of using names, I'm using a relation R with attributes A, B, and C. Now, from a given set of function dependencies f, where A determines B and B determines C, what can your logic imply? You can imply that since A determines B and B determines C, then A also determines C. A determines A, B determines B, and C determines C. This list can get really big if you have 10, 20, or 100 attributes. Let's imagine it from a set theory perspective, that we have a set F, which are a set of dependencies. A determines B and B determines C. Then we have a superset with all the logic implied dependencies, where A determines C, A determines A, B determines B, and C determines C, which we are going to refer as F closure. F closure is then a set of function dependencies logically implied by F. Now let's take a tiny break and talk about keys. A key determines all the other attributes in a relation, right? Keys can be one or multiple attributes. You can pick all the attributes in a relation and make them the key, but that would not be efficient. You want to reduce all those attributes to a minimum point of reference. So what we need is more than a key. We need a candidate key. In order for a key to be a candidate key, it must, just like I said it before, determine all the other attributes in a relation, but also at the same time be minimum. For now, just bear with me and keep just two rules in mind. An attribute X is a key if it functionally determines all the attributes in R, and if it is minimum with respect to condition 1. Let's go back to our relation R. If you want to pick a key with only one attribute, you have three choices, A, B, or C. If your key needs two attributes, again, you have three choices, AB, AC, BC. And finally, if you need all three attributes, you are left with only one choice, ABC. So from only three attributes, we have a total of 7 possible combinations for a key. Now let's imagine that we had 26 attributes in our relation R. Things start to get a little complicated, so I will use a formula to calculate possible combinations where the order of the attributes is not important and without any repetitions. For example, A and B and A are treated the same and they don't repeat. So keys with only one attribute will obviously have 26 choices to choose from. Two attribute keys will amount to 325 possible keys. 5 attributes would amount to 65,780 keys. I will just tell you that in the end, the total of possible keys amounts to 67,180,863 keys. As you could see, it is impractical to determine keys by a trial and error process. What is really needed is a mechanism that allows you to rather find out if function dependencies are inside the set F closure or outside F closure. Then we will be able to define candidate keys in terms of those dependency sets. So now I will introduce Armstrong axioms. What exactly is an axiom? The dictionary definition that catch my attention is the third one, a proposition that is assumed without proof for the sake of studying of the consequences that follow from it. All the work is done by studying the consequences of an axiom. Armstrong axioms are made of three distinct axioms: reflexivity, augmentation, and transitivity. What is reflexivity? Let's say that if A and B are attributes in a relation and are also a subset of attributes A, B, C, then we can also say that attributes A, B, C functionally determines attributes A and B. Augmentation is when, let's say, we have an attribute A functionally determining B, By augmentation, we can add one same attributes to both sides, and that would still be a valid function dependency. And the third axiom of Armstrong is transitivity. If attribute A function determines B and B function determines C, then A must function determine C. One aspect of Armstrong axioms is that they are sound. This means that if we have a set of function dependencies F, and we have a F closure, which is a set of all the function dependencies that we can logically imply from F, and if we apply Armstrong's actions to F, we are not going to find any set of function dependencies that go outside F closure. You only find things inside F closure. Another aspect of Armstrong axioms is that they are complete. This means that if you apply Armstrong actions to F, we are going to find all the functions dependencies set that exists. From the three Armstrong's axioms, reflexivity, augmentation, and transitivity, we can derive three rules called inference rules. The first one is named union rule, the second one is named pseudo-transitivity, and the third one is called decomposition. Let's talk about the first rule, union inference rule. Here we have a pair of function dependencies, A determines B and A determines C. Since they have the same side, you can keep the attribute A and union the attributes B, C. Now we have an attribute A that function determines B and C. The next inference rule is pseudo-transitivity. Let's say that an attribute A functionally determines B and F closure, and CB determines D and F closure. In this case, all we have to do is to replace B by A, so we can derive to CA determines D. And the last inference rule left is decomposition, which works the opposite of the union inference rule. In this example, all we have to do is keep the left side and decompose the right side. An attribute A function determines B, and A also determines C. Let's take a look at this schema R with attributes A, B, C, D, and E, and a set of given function dependencies where A determines BC, CD determines E, B determines D, and E determines A. I will start by using Armstrong's first axiom, reflexivity. By reflexivity, an attribute determines itself. We can logically imply that A determines A, B determines B, C determines C, D determines D, and E determines E. Using the inferential rule decomposition, since A determines BC, then I can logically imply that A determines B and A determines C. Now, I will use the transitivity axiom to logically imply that since A determines B and B determines D, then A determines D. The union inferential rule let me logically imply that since A determines C and A determines D, then A functionally determines CD. Using the transitivity axiom, I'll logically imply that because A determines CD and CD determines E, then A functionally determines E. Now, I can use the union inferential rule to logically imply that since A determines A determines B, A determines C, A determines D, and A determines E, then A must functionally determine A, B, C, D, E. Again, the transitivity axiom allows me to logically imply that since E determines A and A determines A, B, C, D, E, then E also determines A, B, C, D, E. Once again, transitivity will allow me to logically imply that since CD determines E, then CD also determines A, B, C, D, E. Now, I will use the augmentation axiom to say that since B determines D, and if I add the same attribute to both sides of this function dependency, in this case attribute C, Then I can derive to a valid function dependency where BC determines CD. And finally, using transitivity axiom, I can logically imply that since BC determines CD and CD determines E, then BC functionally determines A, B, C, D, E. Now, remember that a key must say everything about all the attributes in a relation. By knowing this, we can say that the following attributes, or set of attributes A, E, C, D, and BC are candidate keys for our relation R. But a key also must be minimal. It must be the minimal set of attributes that tell us everything about the records in a relation. So that leaves us with the attributes A and E as the best candidate keys. And that's how I can explain the purpose of Armstrong's axioms. They allow us to use a set of given dependencies to logically imply all the function dependencies inside F closure, helping us to find out the best candidate keys, eliminating the impractical and almost impossible trial and error